Hello everyone. Today's lecture we shall have a look at the activation functions in neural networks. So I have shown a neural network, the basic structure of neural network, and as you can see here there are some inputs which are present x1, x2 up till xn. Each of them have been assigned weights w1 to wm, and then this is your summation. So we will be taking the summation of the inputs, and the bias also is shown. So this is one particular neuron, and in this neuron we have got two things. The first function is summation and the second one is activation function. So first what will be done is that you will be calculating the sum of the inputs, that is x1 w1 plus x2 w2 plus xm wm plus the bias. And here bias, the weight is not shown, but the weight also can be assigned to the bias. After that, so this what we calculate is called as net. As I have already told you, that this net is given to an activation function, and this activation function is denoted as f of net. So what is this activation function? Now this particular summation function, or it is called a summing function, it is very easy to understand that it will take the inputs, multiply by the weights of the inputs, and then add. But what will this activation function do? So that we are going to see in this particular presentation. So as you can see here, activation functions are mathematical equations that determine the output of a neuron in a neural network. So this is a neuron. This is a neuron, and this neuron, for this particular neuron, the activation function will determine what will be the output. So the sum of the weighted inputs, that is, this is the sum of the weighted inputs that is applied with an activation function to obtain the response. So, okay, the activation functions usually help us to normalize the output in between 0 or 1 or 1 and minus 1. So this is not always the case, but in most of the neural networks, the output is expected to lie in between 0 or 1 or in between minus 1 and 1. But this is not always the case. Then there are two types of activation functions, linear and non-linear activation functions. And non-linear activation functions are usually used in a multi-layer neural network. For neurons in the same layer, same activation functions are usually used. And then activation functions can be classified as hard limiting and soft limiting activation functions. So all the details about this, the difference between linear and non-linear, hard limiting and soft limiting, you will come to know once we look at the activation functions one by one. So we'll go to the, so these are some of the activation functions. I have briefly noted down, put up this table, and here you can see the graphs for the different activation functions. So this is a unit step function. This is, you must be already knowing what is a unit step. So for the unit step, f of net is equal to 0 for net less than 0. So for net less than 0, the output is 0, and for net greater than or equal to 0, the f net is equal to 1. It is high. Then Signum function, just the difference is that here the output is lying between 1 and minus 1. So f of net is equal to minus 1 for all negative values of net, that is net less than 0. And for net greater than or equal to 0, it is 1. Then there is a very simple function, that is linear function, f of net is equal to net. That is, you will be getting a line like this, and then you have got this logistic function, sigmoidal functions, hyperbolic tangent functions, and ReLU function. So we shall look at these functions a little later, but first we shall go to the next slide and see. First we shall have a look at the identity function or the linear function. So it is of the form f of net is equal to net. So if at all I draw the graph of this particular function, how would I get it? Here, this side it is net, and this side it is f of net. So what is told is that f of net is equal to net. So when f of net is equal to net, the graph will be of the form like this. So this is the activation function. So it is as good, and why it is called identity function? Because it is as good as the output is equal to the net. That is, whatever you are feeding to the activation function, that is net, the same thing is the output. So if at all your input is 1, that is net is 1, then f of net is also 1. Okay? So this is what, this is why it is called as a identity function. Now, what is the range of this particular function? The range of this particular function is from minus infinity to infinity, because the output can span between minus infinity to infinity. The input is also ranging between minus infinity to infinity, so the output also ranges from minus infinity to plus infinity. So this is the first function, that is the identity function. Usually this function is not much used in neural network. I will tell you why. But certain places it can be used. I am not saying that it may not be used, but very rarely it is used. We move on to the next activation function, non-negative identity function. We have already seen what is the identity function and how in identity function what we have seen is that f of net is equal to net all throughout. That is for all net. Now, what happens is that this is a non-negative identity function. Now, previously in identity function, what we had was that the graph was like this. So net and f of net. So every time for positive values also of net, the output was equal to net, and negative values also, these are the negative values of net, the output was equal to, f of net was equal to net. But here what happens is that, so it is identity function because output is equal to input. Input is nothing but net, whatever is being presented to the neuron. So there is no activation function sort of which is involved here. But now what happens is that it has to act as identity function only for non-negative values. So what I mean to say is that only for positive half cycle I should be getting this particular value. It is the positive, not I wouldn't say positive half cycle, but only for the positive value of net, f of net is equal to net, and for the negative values of net, f of net is equal to 0. So this particular place, f of net is equal to 0. So this is what is a non-negative identity function. So it acts as an identity function only in the positive range. So it is an identity function only in the positive range, or it is a linear function in the positive range. It is also called as rectified linear unit function because it is a linear function. Okay, it is a linear function, but only for the positive values. So what is the meaning of rectified? So whenever anything is only, rectifier does what? Wherever there is positive half cycle and negative half cycle it removes and only keeps a positive half cycle. So similarly here we have the positive values and the negative values are removed and only the positive values are kept. So that is the reason it is called as rectified linear unit function. So The short form of it is ReLU, that rectified linear unit function. So here f of net is equal to net, and here f of net is equal to 0. Is that clear? So now, what is the range of this particular function? The range of this particular function is from 0 to infinity. The range of this function is from 0 to infinity, whereas for the previous function, identity or linear function, the range was from minus infinity plus infinity. So now, we shall take one equation and try to see whether this equation holds true for this. So I would write this equation as f of net is equal to maximum of 0, net. Now what is the meaning of this particular function? It means that if at all net is higher, then the output will be net. If at all 0 is higher, then the output will be 0. So we'll take an example and say that net is equal to say 1. When net is equal to 1, what will be f of net? F of net will be maximum of 0, 1. So what is the maximum value between 0 and 1? Obviously it is 1. So here f of net is equal to 1 and net is also equal to 1. If at all we take net is equal to minus 1, what will be f of net? F of net will be maximum of 0, minus 1. So here, what is the maximum? It is 0. So because net was negative, the answer is 0. So as goes by the name, it is a non-negative identity function. So if at all there is any negative value which comes, then the answer will be 0. But it is not going to be negative value. So f of net will not be negative, it will always be positive, or at the most it will be 0. Now what is the advantage? This particular function is used in convolutional neural networks. Now this is a recent trend, convolutional neural networks and deep neural networks. So this particular function finds its applications in deep neural networks and convolutional neural networks. Then the function is continuous and increases and is monotonic, and its derivative is also monotonic. So function is continuous. What will be the derivative of this particular function? Function is a continuous function. Yes or no? It is continuous. And what is the derivative of this function? Derivative of net will be what? Derivative of net will be 1. So it is the function is monotonically increasing function. So function is monotonic. Monotonic meaning what? It is going on increasing. If at all a function is increasing and decreasing, it is not monotonic. It has to be continuously increasing in whatever shape, then it is called as a monotonic function. So the function is monotonic and its derivative is also monotonic. Now what is the disadvantage of this particular function? Disadvantage of this particular function is that disadvantage is that it doesn't map the negative values on the graph. For net is less than 0, it produces 0 output. And hence it reduces the ability of the model to fit or train from the data properly. Because it is not going to map the negative values to negative, it will be mapping them to 0. That is the reason what will happen is that it will not be able to train the data properly if at all the data is made up of a lot of negative values. So that is the disadvantage of this non-negative activation function, as rectified linear unit function. Is that clear? Next we will go to the constant function. Now what is the constant function? It is of the form f of net is equal to c for all net. Okay, this particular sign which I have used, it means that it is for all net. For all. Okay, I hope you are aware about it. In the previous slide also it was there. So how will I plot this particular function? If at all I have net as the x-axis and f of net as the y-axis. And what will be the function? Where we have c somewhere here. So f of net is equal to c. So f of net is equal to a constant. Okay, although my line is some crooked, but it is constant. So for any value of net, it may be for f of net is equal to 1, for f of net is, for net is equal to 1, for net is equal to 2, for net is equal to 3, net is equal to 4. Every time the output will be equal to the constant c. Now, why this particular, now in this particular neural network, now in most of the neural networks, the activation functions whose output saturate are of interest. So constant activation functions is not used. Now what is the meaning of output saturates? You'll have seen saturation of a transistor, maybe a transistor as a switch. The output is, when the output is in the saturation region, meaning we get a very high output, and when the output is in the cutoff region. So basically there are two regions. So one region you get a high output, one region you get a low output. So something like that should be the response of a neural network. We should be getting, there should be say two levels, and the output should saturate finally at a higher level or at a lower level. So the levels may be 1 and -1, the levels may be 0 and 1, the levels may be anything. But what we are interested is that the output should be lying between any two levels. And it should be bounded by these two levels. It cannot, in the previous slide also, if at all you see the linear function is going from right from -infinity to +infinity, the output. Here what is happening is that the output is remaining constant, so it is not lying between any two values. It is fixed at one particular value. So again, this type of activation function will not be used much in a neural network. We'll go to the next activation function, step function. So what is the meaning of step function? We shall take a look at what is a step function. So we have net as the x-axis and f of net as the y-axis, and here I write step, meaning we know what is the step function. So I shall just draw the step function. This is just one step function. So in this case there are two states. This I would say as the on state, and this I would say as the off state. So what is the value of this? Okay, I would not just have to wipe it off. So what is this value? Say I have a value here A, this particular point, and this particular point the value is B. And here this is a C, particular point. So what can I write as equation? What is f of net? F of net is switching between two values A and B. So sometimes f of net is equal to A and sometimes f of net is equal to B. So when is f of net equal to B? It is equal to B when it is in the on state. So when I mean to say on state, it means that net should be greater than or equal to C. So here, whenever net is greater than or equal to C, that is when the output will be equal to B. And when net is less than C, the output will be equal to A. So this, I say that this is the on state, this is the on state, and this is the off state. So basically step function meaning, if you know what is the meaning of a step, so this just resembles a step. So this is a step function. Now we go to the next function. Now this is a very generalized step function wherein I have defined it in terms of A, B and C, and I have not told you what are the values of A, B and C. If at all we go to the next slide, you will see what is a unit step function. So if at all you know what is a unit step function, or you can, from the previous slide itself, you can guess what is a unit step function. So unit step function would be somewhat like this. You already may have studied in different subjects what is a unit step function. So what happens in a unit step function? The output can be either 0 or it can be 1. So f of net is equal to 0 when net is less than 0. That is, this particular region, it is 0, and f of net is equal to 1 for net is greater than or equal to 1. So this is my 1, this is 0. So the two levels in between which it switches is, it is switching between 0 and 1. So for net less than 0, it is equal to 0, and for net greater than or equal to 0, it is 1. So this particular function, if at all you see, as compared to the previous function, in the previous function, this level was called as A, and this level was called as B, and this level on the net side was called as C. So what will be A here? A is equal to 0, B is equal to 1, and C, that is the threshold, is equal to 0. So this value was C there. So that is equal to 0. So I'm not saying that you should remember in the form of ABC. Even if you remember this equation, it is more than enough. F of net is equal to 0 and this particular graph. You may not remember in terms of ABC, but I'm just telling you. So next we go to the Signum function. Now Signum function, there is a slight change. Signum function, the two levels which are there, they are -1 and 1. So in place of this 0, you will have -1, and in place of this 1, you will have 1 itself. So if at all I draw the graph of Signum function, then I will get it like this. So f of net so the two levels will be of this form. When net is greater than or equal to 0, then the value is 1, and when net is less than 0, the value is -1. So here, if at all you want, A will be equal to -1, B will be equal to 1, but C is still equal to 0. So these are two very, very important functions which are used in neural network, and these are binary functions. So you can say, yeah, these are binary functions because the output lies between, the output can either be 0 or 1 or -1 and 1. In this case, it is called as a unipolar function, and or it can be also called as unipolar binary function or unipolar step function, and in this case it is called as bipolar step function. So bipolar because it's got both the polarities, -1 as well as +1. Whereas here you have only single polarity, it is not negative, it is only positive. So I'm telling you unipolar and bipolar because in different problems, different terminology could be used. So you should not get confused. Is that clear? So this is also called as unipolar discrete neuron and bipolar discrete neuron. So this is this activation function is for unipolar discrete neuron. This is for a bipolar discrete neuron. Discrete neuron because the output is only lying or switching between two different values. Okay, we have seen Signum functions. Now what are the disadvantages of Signum function? Disadvantage is that the Signum function is not differentiable. If at all you want any function to be differentiable, there should be no discontinuity. This you would have studied maybe in maths earlier. So what happens is that in case of Signum function, there is a discontinuity. And where is the discontinuity? Discontinuity is here. So the signal is not a continuous signal, and because it is not a continuous signal, it is not differentiable everywhere. So because this particular function is not differentiable, the Signum function or step function it is having a disadvantage, so you cannot find the derivative of Signum function. That is the reason it may not be used everywhere in case of neural networks. But it has got the feature. Now the advantage, if at all you see, it would be that it saturates. Now I have told you that the activation function should be such that it saturates. So there are two levels, as you can hear, +1 and -1, and the output saturates at this particular level 1 or -1. So that means that it saturates. But it is not differentiable, and that is the reason it may not be used. But one more point which is to be noted is that although the output saturates, it does not increase or decrease to the values whose magnitude is excessively high. So, it is not going to, there is no variation for all the inputs. Say, if at all the input is 1, the output is 1. Input is 2 also, the output is 1. Input is 3 also, the output is 1. If the input is 1000 also, the output will be 1. So whether the input is large or whether the input is small, it produces only one particular output, that is high. Similarly, if at all the input is negative, -1, -2, and maybe even -10,000, the output will be -1. So it doesn't change with respect to the input. It doesn't change with respect to the input. It will just be having two values, +1 or -1. So a binary step function is also called as a threshold function. So binary step function is called as threshold function. So, or it is called as Heaviside function. Okay, I had this binary step function is nothing but this one, unipolar step function. This is called as a threshold function or a Heaviside function. So this is just for your information. Now, we shall go to the next part, that is, ramp function. Ramp function, I shall be drawing the ramp function. So as you know, what is the meaning of a ramp? So the function is somewhat like this. This is a ramp function, and it has got a kind of a ramp which is present here. So if I tell you, so I indicate these points as A, B, and this is C, and this is D. So how many states does this function has? The previous function had got only two states, high state, the low state, or the on state and the off state. This one has a stage which is intermediate, and that particular place it is a ramp. So it is a off state. Here I could say this is a off state, this is the on state, and this particular state is the linear state. So it is there is a line, it is linear. So in that case, maybe net, what is the value of f of net, we have to find out. So if at all we look at this particular function, can you all tell me what will be the, you all can tell me what will be the equation of f of net? We can write the equation of f of net in terms of f of net is equal to A. F of net is equal to B. So when is f of net is equal to A? Is when net is less than C. That is here, this particular case, this particular case, you can see that it is equal to A. Then this side, beyond say D, we can see that f of net is equal to B. You can see this particular level here, f of net is equal to B. And here f of net is equal to A. That is less than C. Now, so I can write this as when net is greater than or equal to B. Now the main concern is what will be the value of net in between C and D, that is this linear region. So how can you find out? you already know how to find the equation of a line. So we will be using the same technique to find out the equation of a line, and we shall be using this. What is the equation of a line? Do you know? In y minus y1 upon x minus x1 is equal to y2 minus y1 x2 minus x1. This is one particular form of the equation. This is a two-point form where the 2 points are y2 and y1. So the first point is here and the second point is here. So what is the first point? First point is nothing but what is x net, net and f net, because it is not x and y, it will be net and f net. So here also this equation here, it will be nothing but y is nothing but f net and x is nothing but net. So first point is nothing, this is not the first point. First point is nothing but C, that is here, C comma A. And second point is nothing but D comma B. So when I write this particular equation here, so what will I get is that this will be nothing but x1, y1, this will be nothing but x2, y2. So I replace here, y is nothing but f of net minus y1. What is y1? A. And x is net minus c is equal to b, that is y2 minus a, d minus c. So this, from this I can write the equation, I can take a certain thing on the other side, f of net minus a will be equal to b minus a, d minus c into net minus c. Sorry, net, there is no bracket here. Sorry, there is no bracket here. It will be net minus c. From this we can write f of net is equal to b minus a, d minus c, net minus c plus a. So this will be the equation. Sorry, I have not written the minus sign. Net minus c plus a. So I have to write the same thing here. That is, f of net will be nothing but b minus a, d minus c, net minus c plus a. So maybe I can just, rather than squeezing it up, I can take it on the other side. Okay. So I think this is fine. So this is the ramp function and this is the way it is defined. Now we shall go to the special cases of ramp function where, we will be having c, d, a, 0, whatever the values we will be putting. So here there are, we'll go to the next part wherein, this particular graph, in this c is equal to 0, d is equal to 1, a is equal to 0 and b is equal to 1. So how we would get this? So this is net, this is f of net, and we shall be drawing the graph. Okay, so this point is nothing but 0 and this point is nothing but 1. So this is 1 comma 1 and this is 0 comma 0. So in between 0 and 1 the output is allowed to vary with respect to the input, and otherwise the output will be equal to 1. So how can I write the equation? F of net will be what? F of net will be equal to 0 when net is less than 0. F of net will be equal to net, that is linear function, when 0 less than 1. So when it is lying between 0 and 1, f of net is equal to net, and then net greater than or equal to 1, greater than or equal to 1, it will be 1. So this is another type of a function which is a ramp function, but a ramp function with this particular characteristic, c is equal to 0, a is equal to 0. So this is also a ramp function but with a special characteristics. Now again, if at all I want, I can write it in another form. Now this you will be using for some problems later. So f of net can be written as minimum of 1 comma maximum of 0 comma net. So this is another function which can be used for representing the same graph. So I have shown two ways of writing the equation. This is the first way, this is the second way. So this is the equation. This is, with one line you can write the equation. But what does it mean? F of net will give you the value which is minimum. Now whether it is true, we shall take a look at an example and see whether this equation holds true. So we shall take an example, net is equal to 2. So when net is equal to 2, what should be the answer? Ideally, by looking at this, net is equal to 2, meaning answer should be, f of net should be equal to 1. But we shall check. How we check is that, what will be f of net? It is minimum of 1 comma maximum of 0 comma 2. That is net. So what is the maximum between 0 and 2? What is the maximum value between 0 and 2? Maximum value is 2, right? So what this will reduce to, this will become minimum of 1 comma 2. Now, what is the minimum value out of this 1 and 2? Minimum value is 1. So, when net is equal to 2, f of net is equal to 1. So the equation is correct. We'll take another example and check. And that example we shall take as net is equal to something else. Say we'll take net is equal to 0.7. When we take net is equal to 0.7, f of net will be nothing but minimum of 1 comma maximum of 0 comma 0.7. Now what is the maximum value? What is the maximum between 0 and 0.7? It is 0.7. So it will become minimum of 1 comma 0.7. And what is the minimum between 1 and 0.7? Minimum between 1 and 0.7 is 0.7. So net is lying between what here? A net is lying between 0 and 1. And when it is lying between 0 and 1, the output is equal to net. So here, when net is equal to 0.7, f of net is also equal to 0.7. So this condition is also getting fulfilled. Take another example where net is, something will take negative value. Net is equal to minus 1. So when net is equal to minus 1, what happens is that f of net will be minimum of 1 comma maximum of 0 comma minus 1. So what is the maximum value between 0 and minus 1? Obviously it is 0. So it will be minimum of 1 comma 0. What is the minimum value between 1 and 0? Answer is 0. So because net is a negative value, net is minus 1, that is here, the answer f of net is equal to 0. So you remember this particular equation, it will be used somewhere later on and it will be useful. So this is a ramp function. Similarly, now we can have the bipolar ramp function. Now whatever ramp function which was discussed earlier, that is this one, was a unipolar ramp function. Okay, so this one you can call it as a unipolar ramp function. Similarly, we can have a bipolar ramp function. In case of bipolar ramp function, the 2 points of interest are 1, 1 and -1, -1. In the previous case, it was 0 and 1, so it was only in one direction. Now it is a bipolar ramp. So how shall I draw the waveform? So from -1 to 1, it is a linear function, and beyond 1, it is constant, and the value is 1, and less than -1, the value is -1. So if at all we want to write f of net is equal to 1 for net greater than 1. F of net is equal to net when net is lying between -1 and 1, and f of net is equal to -1 when net is less than -1. So this is the equation. Now, unlike step function, the ramp function is continuous over a small interval. So here also that continuity we have to check, and we have to check for whether the output saturates. So here, as you can see, the output saturates to a value capital 1, and for the negative inputs to -1, but in between it is linear. So what happens is that the output saturates for positive values as well as negative values, and it is continuous, but there are some it is continuous at 0, which was not happening in the previous case. So although there is it is a compromise between although you get this, but you are losing the simple on-off operation. So although the function is continuous, this is a continuous function, but the function is not differentiable. So the function is a continuous function, there is no discontinuity, but at this particular point the function is not differentiable. So rest everywhere it will be differentiable, but at this particular point C and D the function will not be differentiable. So that is a disadvantage of ramp function, and that is the reason we go in for sigmoidal functions, which we shall see next.